This is Jabbie. Today we're doing Electrophilic Aromatic Substitution of Benzene in 43 questions.
Only 43 questions, you say?
Yeah,
Only 43 questions.
question number 1. What kind of catalyst is used in monosubstitution of benzene and for what purpose? A Lewis acid. A Lewis acid reacts with the reagent to generate an electrophile. Question number 2. Write an equation showing an example of how this happened. This right here is an example showing that. In the nitration of benzene, nitric acid is used as one of the reagents. The Lewis acid in this equation is sulfuric acid, H2SO4, and this is used to cleave the electrophile from nitric acid. Question number 3. What are the 3 steps in monosubstitution of benzene? Step number 1. Or steps number 1, because there are kind of 2. So the first one is the generation of the electrophile. Next is electrophilic attack of the pi electrons on benzene. So that electrophile can collide with benzene's pi electrons, and a pair of those pi electrons will then form a sigma bond with that electrophile. A resonance stabilized carbocation called a rhenium. Sorry, always get that wrong. That collision leads to the formation of a resonance stabilized carbocation called an rhenium ion. Step number 2. A hydrogen ion is removed from that carbocation, generating the product. Step number 3. The hydrogen ion removed is used to regenerate the Lewis acid that was used in the beginning to form the electrophile. Question number 4. Describe the first step of monosubstitution of benzene using an example. Let's use the chlorination of benzene. Before anything can happen, the electrophile needs to be generated. In this example, the Lewis acid we use is iron 3 chloride. So the Lewis acid reacts with chlorine to generate a chlorine electrophile. That chlorine electrophile then attacks the pi electrons on benzene, leading to the resonance stabilized carbocation we spoke of earlier. Question number 5. Describe the second step in monosubstitution using the same example. As mentioned before, the second step is the removal of that hydrogen ion from the carbocation formed and the generation of the product. In this case, the product is chlorobenzene. Question number 5. Describe the third step in monosubstitution. Well, the third step is the regeneration of the Lewis acid used to generate the electrophile. In this case, hydrochloric acid is also generated. Question number 6. Explain how we are able to deduce that the first step is the rate determining step. That right there is the slowest and the rate determining step in monosubstitution of benzene. A carbon deuterium bond is stronger than a carbon hydrogen bond. Both benzene and per-deuteriobenzene undergo electrophilic aromatic substitution at the same rate. If the rate determining step had anything to do with the cleavage of that CH bond, then what we would observe is that per-deuteriobenzene undergo electrophilic aromatic substitution at a different rate to benzene. Because no kinetic isotopic effect is observed, we can draw the conclusion that the rate determining step of monosubstitution of benzene is in fact the attack of the electrophile on the pi electrons of benzene and not the cleavage of the hydrogen. Question number 7. Give examples of the types of monosubstitution benzene can undergo. Acylation, sulfonation, halogenation, alkylation, nitration for the nation. But you got me waiting, but it don't matter because I'm skating. Question number 9. Describe the nitration of benzene. In the nitration of benzene, nitric acid is reacted with sulfuric acid to generate the electrophile. Then that electrophile attacks the pi electrons on benzene, forming that resonance stabilized carbocation. That carbocation then loses a proton to form nitrobenzene. That lost proton is then used to regenerate the Lewis acid. And that's it. Question number 10. What is the alkylation of benzene often referred to as? Friedal-Crafts alkylation. Question number 11. Describe the steps in a Friedal-Crafts alkylation using an example. So we're going to use 2-chloropropane reacting with benzene and aluminium chloride as the catalyst. So 2-chloropropane will react with aluminium chloride to generate the electrophile, which is an alkyl cation. That alkyl cation then attacks the pi electrons on benzene to form the rhenium ion. That rhenium ion then loses a proton to form the desired product, an alkyl benzene. In this case, an isopropyl benzene. The hydrogen lost is then used to reform the Lewis acid. and that is an example of a Friedal-Crafts alkylation. Question number 12. What is a problem that can occur in Friedal-Crafts alkylations? In Friedal-Crafts alkylations, the addition of that alkyl group can activate the ring to further substitution, to second substitution, which can lead to the formation of undesired products. Question number 13. How is this avoided? We avoid this by using an excess of the aromatic compound. Sorry. 14. Are there any other problems that can occur in Friedal-Crafts alkylation? Yes. Question number 15. What are these problems? In Friedal-Crafts alkylation, something called a rearranged product can occur. This happens when the alkyl cation rearranges itself without permission because it wants to be more stable. If you've watched my video on SN1 and SN2 substitutions, then you kind of maybe get what I'm talking about. So when there is an alkyl cation, a 1-2 shift can occur. This can be a shift of a methyl group or a hydrogen atom, and this is the alkyl cation trying to become more stable. When this happens, a rearranged product can occur. We don't like rearranged products because that's not what we want. We know what we want and it ain't a rearranged product. 16. Give an example on how this can occur. Here we see chloropropane reacting with a Lewis acid to generate the electrophile, that is the carbocation. That is a primary carbocation that is generated. Here we see that same electrophile undergoing rearrangement to form a secondary carbocation. It does this because it's more stable for it to be a secondary carbocation than a primary carbocation. However, this will lead to a rearranged product, because as you can see, they will form two different types of alkyl benzenes. Question number 17. What is another way in which desired alkylation can be achieved without rearrangement? So you can also achieve this by using alkenes in the presence of hydrochloric acid and aluminium chloride, which also generates an electrophile, and in some cases, a more stable one. Question number 18. Describe another method in which the alkylation of benzene can be accomplished. This can be done through a Friedal-Crafts acylation followed by reduction. Question number 19. Using an example, describe the generation of the nucleophile in the acylation of benzene. This right here is a generic way of showing how a Lewis acid is used to generate an electrophile from compounds containing acyl groups. In this case, the electrophile is an acylium ion. It essentially generates the electrophile in the same way it does with other compounds. 20. Comment on a characteristic of the acylium ion. So the acylium ion is resonance stabilized. There are 2 lone pairs on the oxygen of that carbonyl group. Because of that, the acylium ion is able to sort of resonate between 2 different structures. This allows it to become resonance stabilized. 21. Using an example, describe and explain the acylation of benzene. Let's use the reaction of benzene with acetyl chloride to show this. So acetyl chloride reacts with the catalyst, aluminium chloride, to generate the acylium ion, i.e. the electrophile. That acylium ion then attacks the pi electron cloud on benzene, leading to the formation of the resonance stabilized carbocation, i.e. the arrhenium ion. That arrhenium ion then loses a hydrogen to form the desired product, which in this case is acetophenone. The proton loss is then used to regenerate the Lewis acid used in the beginning, and that is the acylation of benzene. 22. Describe the sulfonation of benzene. The sulfonation of benzene occurs with the reaction of benzene with fuming sulfuric acid, and that is the equation of the reaction, of which the product is benzene sulfonic acid. What are 2 characteristics of this reaction, and what benefits are drawn from these characteristics? There are 2 characteristics of this reaction. This is a readily reversible reaction in water. And number 2 is that the sulfonic acid group is easily displaced, making benzene sulfonic acid a good intermediate for other synthesis. 26. What is known as an activating group? An activating group is a group that makes the aromatic ring more susceptible to further electrophilic substitution. So it basically facilitates a better environment for electrophilic attack. 27. What is known as a deactivating group? A deactivating group causes the aromatic ring to be less susceptible than benzene to electrophilic attack. This basically does the opposite of what an activating group does. 28. How else can the group already on the ring affect second substitution? So that first group on the ring can also influence the position at which second substitution occurs. 30. What is a meta-director? A meta-director or an M-director is a group that influences second substitution to occur at the meta position on the ring. 31. What is an ortho-para-director? A group that influences second substitution to occur on the ortho or para positions of the aromatic ring. 32. What are two common characteristics of OP directors? And are there any exceptions? All OP directors have a lone pair of electrons except aryl and alkyl groups. All OP directors are activating groups, i.e. they activate the ring, except halogens, which are deactivating to the ring. 33. In what ways do OP directors behave as ring activators? OP directors are able to donate a pair of electrons by resonance. This increases the resonance stability of OP intermediates and it makes the ring more susceptible to electrophilic substitution. Their contribution in increasing the resonance stability of their intermediates make those intermediates of lower energy and more stable. This means that the rate of reaction is much faster and therefore the reaction itself is more favorable. 34. Use an example to explain this in more depth. So I'm going to use the nitration of phenol to try and sort of show you how this works. The OH group on phenol is an OP director. Therefore, it will influence secondary substitution at either the ortho position or the para position on the aromatic ring. So I'm using the ortho position to demonstrate how the phenol groups adds to the resonance stability of the intermediate of that reaction. In the ortho nitration of phenol, the following resonance structures are possible. Over here you can see how oxygen donates a pair of electrons to add to the resonance stability of the intermediate. It essentially helps to share that positive charge, decreasing the energy and increasing the stability of the intermediate. 35. How are halogens different from other OP directors? Although halogens are OP directors, they are deactivating groups, i.e. they deactivate the ring, or they make the ring less susceptible to electrophilic attack. We say that this is an exception because most OP directors are activating to the aromatic ring and not the opposite. 36. I'm tired. Use the comparison with an activating ortho-para director to explain why halogens are deactivating. Halogens are electron withdrawing groups, but so are many of the other OP directors. For example, an OH group is an electron withdrawing group. So what makes an OH group activating to the ring when halogen is not activating to the ring? Let's look at the resonance structure in which the oxygen in phenol donates a pair of electrons to add to the resonance stability of the intermediate. Let's look at that. So that bond there, that double bond there, occurs from an overlap of the 2p orbital of the carbon there and the 2p orbital of the oxygen. Those 2p orbitals are similar in size, therefore maximum overlap can occur. This maximum overlap provides added stability. Let's look at the resonance structures in which the halogens donate a pair of electrons to increase the stability of their intermediates. So here we have the nitration of chlorobenzene, nitration of bromobenzene, and nitration of iodobenzene. Although all three of these halogens donate an electron, thus actually adding to the resonance stability, it is not the same as when it happens in phenol. The difference is the orbitals used to form these bonds. With chlorobenzene, it's the overlap of the 2p orbital of carbon with the 3p orbital of chlorine. In bromobenzene, it's the overlap of the 2p orbital of carbon with the 4p orbital of bromine. And in iodobenzene, it's the overlap of that 2p orbital in carbon with the 5p orbital of iodine. All three of these orbital overlaps are between orbitals of different size. Because they are orbitals of different size, this means that maximum overlap cannot be achieved. Their overlap is less effective. This means that these intermediates are less stable and of higher energy. It also means that the rate of their reactions are slower, therefore the reaction less favorable, explaining why it is deactivating. Question number 37. Discuss the OP director traits of alkyl groups. Alkyl groups are electron-releasing groups. Because of this, they add to the electron density of the aromatic ring, making the ring more susceptible to electrophilic attack. 37. What are two characteristics of meta-directors? Characteristic number 1. They carry a positive or a partial positive charge. Characteristic number 2. They are electron-withdrawing groups. 39. Explain the effects these characteristics have on second substitution. Because they are electron withdrawing groups, they draw electrons towards them, thus decreasing the electron density of the ring. This makes the ring less susceptible to electrophilic attack. You know why? Because electrophiles love electrons. So if they come in at a ring and the ring ain't saying much because another M director is trying to steal all those electrons, they gonna be like, man, they ain't no electrons here. They ain't no electrons here. 40. Comment on the deactivating properties of the M directors. Meta directors actually deactivate all positions on the ring. It's just that they deactivate the meta position the least. So, yeah. 41. Use resonance structures to show how the meta position is the least deactivated. These are the resonance structures of ortho substitution of a ring with a meta director attached to it. These are the resonance structures of para substitution occurring on a ring with a meta director attached to it. And these are the resonance structures of meta substitution on a ring with an M director attached to it. You can see here with ortho and para substitution that the positive charge ends up adjacent to that M directing group that also has a positive charge. This is extremely unfavorable. A positive charge near a positive charge is a no-no. Now you can see here that with meta substitution, that positive charge never ends up adjacent to that M directing group that has the positive or partial positive charge. So once again, M directors deactivate all positions on the ring, but it just deactivates the meta position the least. 42. Describe 3 general rules of the third substitution of benzene. Number 1. If 2 substituents on the group direct an incoming group to the same position, then substitution will occur in that position. Rule number 2. If 2 substituents direct an incoming group to different places on the ring, then the effect of the strongest activator will be exerted. General rule number 3. If 2 groups are meta to each other, then substitution does not normally occur between them. The reason for this is steric hindrance. Whoa, I think we're done. Oh my god. Thank you for watching.
Olga, be sipping,